Okay. So I'm here with MIT PhD Dr. Keith Duggar and the unmistakable Dr. Walid Saba. We wanted to have a bit of a conversation about interpolation versus extrapolation, and this is a bit of a precursor to conversation we're going to have about spline theory with Randall and Imtiaz. So first of all, I want to draw your attention to this animation that's up on the screen now, and it's showing a manifold in a two-dimensional vector space, and it's showing two classes around a kind of circular manifold, and the neural network is learning to partition between those two classes. But what's particularly interesting about this example is part of the manifold has been removed, and the neural network manages to learn the structure outside of the training support. So it's kind of filling in the manifold outside of the training support. And we also visualize the spline partitions which are learned. And of course, you can watch our show about the spline theory of neural networks. But what an MLP does is it partitions an input space into these locally affine polyhedra. Now, we always thought that neural networks were a bit like locality-sensitive hashing tables, and we thought that the extrapolative functionality was purely a function of all of the inductive biases, like the GNN, the CNN, the GCN, the transformers, etc., because what those biases do is they take your training data and they photocopy it everywhere, which allows the neural networks to be interpolative outside of the training support. But what this particular example seems to show is that the neural network can be extrapolative outside of the training support. Now, we need to understand a little bit about what we mean by extrapolation. Do we mean the convex hull? Do we mean the non-convex hull? Do we just mean outside of the training support, whatever that means? Why don't I pass it over to MIT Dr. Keith Duggar for a bit of for a few thoughts on it?
Sure. Well, I mean, we had these conversations previously with LeCun and Balestriero and Chalet as well about what does it mean to extrapolate. And, it's actually surprisingly difficult to define it in such a way that it's fruitful for higher dimension, because we kind of saw like, well, if I'm going to take the definition of, extrapolation to be within the convex or outside of the convex hull, so anything inside a convex hull, the data points is interpolation, then that just immediately obviously breaks down as you go into higher and higher dimension, because that volume becomes, infinitesimal or like exponentially smaller, portion of the sample space. And you could argue for like a different definition, which is, no, I don't want to use the convex hull. I'm going to use the, the axis aligned bounding box. Okay. So just like, if any of its values hit the range of any of the values on any dimension hit the range of a sample on any dimension, then that's interpolation, right? And so you have to kind of figure out like what is my definition here, right? Like of these higher dimension extrapolations. And I don't think anybody really has a good one. Like they don't have one that doesn't just break down one way or the other, kind of in exponentially high dimensions. And we have this, at the end of the day, we're trying to capture this sort of concept that neural networks learn functions in a particular way that starts to break down in a way that we can recognize as human beings, right? Like it breaks down in this kind of generalization sense, or as you get kind of further away in a sense, right? Further away. And how do you define that? Like, how do you define distance in high dimension? I don't know. I mean, when you get further away from the samples, you start to see these problems, right? That it breaks down. And we're trying to capture that notion, but nobody knows how to formalize it, like in a mathematical way that maintains its utility in high dimension and still continues to kind of capture like the intuitive notion of extrapolation versus interpolation. Oh, and I should just point out too, it's even surprisingly difficult in just 2D, because okay, in the animation we've got this little annulus, if you will, or this kind of like part of a ring, right? Well, is it extrapolating just because it's connecting that ring that's kind of well within the range there? I mean, I kind of think more of extrapolation as outside of that ring, not within the range. But on the other hand, okay, if we draw the convex hull, it's outside, but just slightly outside. Is that extrapolation? Or did you mean kind of like a little tube that kind of follows around the thing? And, I mean, it's hard. It's hard to define it even in 2D, it seems.
Well, I mean, I'm not sure why we have to change the definition just because it's not working, in a way. I mean, extrapolation, the definition to me is very clear. It is going outside, and it's difficult in high dimension. Well, it is difficult, but that's what it is. I mean, I just had a thought. Is this all related to adversarial examples? Because I don't believe neural networks, the ones we know, really extrapolate. They expand the possibilities and then interpolate within that, which means they cover invalid stuff. And that's where the adversarial examples live. Which means they're not doing a good job in extrapolating. That's how I see the whole. I don't know if that makes sense.
If I could push back on that a tiny bit, I think we thought, as you just elucidated, and this was what I said previously when we did episodes on spline theory and with Thomas Lux, that it's interpolative and the inductive priors just diffuse the information. They spread it out, they photocopy it. But this example seems to show that this is just an MLP, and it knows all sorts of things about regions outside of the training support. Now, as Keith was saying, we can have a big philosophical discussion about what we mean by extrapolation. And the problem is that Keith can talk to this geometry in 1 dimensions, 2 dimensions, 3 dimensions, 4 dimensions, dramatically different. And we have the curse of dimensionality, which is that the volume increases exponentially with respect of the dimension. But this is something even more than that. I think there's something else that happens when you increase the dimensionality. So what we don't have is a definition that captures the notion of training support, because in this particular example, the support is clearly falling on a manifold. It's human intelligible when we look at it. Why don't we start with your definition, Walid? So you came at it from an information theoretical perspective. You gave me quite a nice definition of extrapolation.
Extrapolation is really inference. It's deduction. It's it's inferring new information from the information you have. It's going outside of what you have and making a valid inference to cover additional data that you have never seen. I don't think the definition is, we can't blame the definition. Extrapolation is inferring outside of what you have seen. It's really deduction.
Right. The problem is, just stick with, 1 dimension for the moment. Like it just keeps it simpler, right? If I give you a sample at -1 and a sample at 1, okay, is 0 new? Because you haven't shown me 0, right? You haven't given me a data point at 0, so why wouldn't 0 be extrapolation? Well, the only reason why traditionally it's not considered extrapolation is that we have a notion of a metric on this line, or I guess maybe more minimally a connected space. So there's like an ordering of the space and it's connected, and there's a betweenness concept, and 0 is between -1 and 1. So traditionally that's the definition of interpolation, right? Which is you evaluate a function, and the single dimensional value x, is greater than or less than all the values that you had. And in a sense, it's kind of arbitrary, right? But it is trying to capture something, which is this inductive bias that we have, that if I give you a bunch of samples, that there's a relationship and kind of a smooth connection between those, and that in between there, it's easier because we're kind of interpolating, whereas outside, as we get further away, it starts to become less and less certain, right? And for real world things and stuff that happens in physics and, samples from actual physical systems, like that makes a lot of sense. Like there is this kind of
Right.
continuity, right?
So this might be related to the other issue.
Well, let's not get to that other issue yet. But let's stick with your point though, because I'm asking you a legitimate question, which is, the definition breaks down pretty easily.
It breaks down pretty easily because you made a major assumption: continuity. Look, the whole idea of
doesn't have to be continuous. I just said it's ordered. Like there's just a
then zero doesn't have to be there if it's not continuous.
Sure.
Look, at the heart of the example you showed is continuity. Otherwise, I don't have to include zero. So these two are related. The fact that you're trying to overread, really, and you're making assumptions that probably are not valid.
Well, but that's my point to you, is the traditional definition of interpolation and extrapolation that you gave either there's one of two things here, Wally, because you said it's data you haven't seen before. Either it's totally useless because every single data that I've seen is either exactly in the sample set or it's new, in which case I'm always extrapolating unless it's the exact same data point you've already told me the answer for. So it's either a useless definition, or it relies on the underlying assumptions that went into the classic definitions of interpolation and extrapolation, which isn't necessarily continuity, but it's ordered. It's an ordered space of some kind of metric.
Then I will modify my definition slightly. I will say extrapolation is deduction, is continuous deduction, or deduction in a continuous space. Like, the challenge really is it's like precision and recall, extending your coverage, but not including invalid points. That's really extrapolation, because you can always extrapolate, right? And do it wrong, right? You agree? I mean, then it's easy.
Well, could we bring in the messiness of vector spaces? Because in high dimensions and in messy examples, what does it mean to extend your coverage? What is coverage?
Your function. Your function, it can be infinite, right? But at some point, basically where is the boundary, right? Where is the boundary of your extrapolation? You obviously want to cover data points that are not in your input. Otherwise, you didn't do any extrapolation. But how far you want to go? Your extrapolation is as good as your extended coverage is. And that's why I think it's related to adversarial examples. Most neural networks they overlearn.
So I think we're kind of all moving, and again, this is what we chatted about before, is that intuitively, I think we all understand, what we're trying to say here. And it's something like, let's just take continuous as the space that we're talking about, since that's where you want to go, and it makes it easier. But just suppose we have some, continuous multi-dimensional space, right? And we got some samples and they're a point cloud in this space. Really, I think the most intuitive definition is that interpolation occurs when you do inference that's nearby, that kind of cloud, like it's close to it somehow. Maybe not like inside, but just right outside of it. It's kind of close to.
And that's the example Tim was
right.
showing.
And in in multidimensional cases, it can even be the case that the interior of the convex hull may be like not sampled at all, because it may actually be quite far away from the shell, that you sampled. So the point is just that interpolation is happening when you're near, in this kind of sense, samples that you had. Extrapolation happens when you're far away. And let me just quickly get to this here. And I don't like the binary distinction. Like, I'm not so interested in having a divide, like that was interpolation, this was extrapolation. But what I'm more interested in, we kind of talked about this back when we were talking about before, is a measure of what percentage interpolation am I doing? Like, this is this sample here is 97%
Right.
extrapolated, 3% interpolated, because if we have that measure, we can start to optimize and compare, methods.
Right.
But can I just quickly...
Or the distance. How far am I going? Like if I'm just nearby, I mean...
Yeah, that's what I mean.
Yeah.
But hold on. Because I wanted to pick up on this word near from Keith. In high dimensions, near is meaningless.
That's why I air quoted
is far
it.
away.
That's why I air quoted it. Because
there's no such thing as nearness. And Keith, I like this line of thinking that you're alluding to, because this is the conclusion we drew when we spoke with Balestriero last time. You start off with this convex hull notion of extrapolation. What's the cache value of that? Doesn't get you very far, does it? And then it leads you to this almost probabilistic or kind of threshold-based notion of extrapolation,
which
in respect of every single dimension.
Which it is within an acceptable error, right? Yeah.
No, I'm with you, Tim. Which is that, that was the takeaway message for me back when we were looking at that paper. Is just that we really don't yet have a good definition of degree of extrapolation, or 1 minus the degree of interpolation, to use that doesn't absolutely break down exponentially in high dimension, and even in 2 dimension is kind of difficult to define. And I think if we had some more sophisticated, generalized notion of this, rather than the classic trivial extensions of 1D, from a convex hull, which is a line segment, to a convex hull, or a bounding box or whatever. Like, we need something better, because then we can start to ask questions like, okay, this particular neural network, on this training set, what percentage extrapolation do we get from it? Like extrapolation accuracy or something. Like, that'd be a really useful metric to have.
But Keith, are you then saying that kind of neural networks don't really extrapolate?
No, I'm saying that a given neural network on a given data set will have a fractional extrapolation for certain regions of the sample space, and the different neural networks will perform more or less extrapolation. Like, some may be doing like only interpolation, or 99% interpolation, and they just break down rapidly, as the extrapolation distance grows, whereas others may be able to field much higher degree of extrapolation, but they may have a lower overall accuracy or something like that. These are all interesting trade-offs.
Right, like transformers are a good example. Sorry, go ahead.
Well, I just wanted to say that this example that we're showing in 2 dimensions, it does update what we were saying before. So in 2 dimensions, the concept of in the training support is intelligible because you can visualize it. And outside of the training support, the MLP is informing regions, right?
Well,
clearly.
Well, and I would say, though, like, if you do draw a convex hull around that data, you'll see that that's basically the border of the convex hull there. And so I'm sure if we had this cool measure that we don't have, if we had it and we ran it on the set, we'd find out that that particular segment in the animation is like 0.2 extrapolation. It's like 0.2. Yeah. Whereas, like, for example, imagine you gave it a different function, like sine of x times y, and you gave it training data for like 0 to 1.2 pi in both x and y, and then it was able to extrapolate that funky curve thing, out to maybe 2 pi in all directions. Then you'd get like an extrapolation score of like 0.8. It's like, yeah, it's doing a really good job out there.
And we should mention as well that
I was going to say that could be a function of the data of the data that you have.
100%.
Yeah. I was going to make that point.
So we were just lucky that we have a very smooth, nice. I mean,
right. But this is so useful because now it's like, imagine we had this fantasy measure, and we train an NLP of a certain class on a certain data set. And we find out, wow, this combination of data and this NLP is like 0.9 extrapolative or something. Sure. Whereas when we just slightly change the data set, like it drops to 0.5. Like, why? Like, what happened?
And by the way, Keith, that has implications on performance and computational work that you might have to do. If you keep track of your extrapolation measure, let's call it, then you might say, wow, this data, I don't need 200 more million data points. You know what I mean? Like the nature of the data is telling me that's enough.
Totally agree.
Yeah.
Yeah.
But to that point as well, so this example I showed you is quite contrived. It's a regular manifold of symmetry. And so as you were saying, there's some regularity in data. And also there's some regularity in just the basic inductive priors of an MLP. An MLP is not a blank slate. It has lots of structure.
Right.
Neural networks, even untrained, can perform massively better than random guessing on many data sets. So there's a lot of structure in there. And a lot of that structure might actually cohere with physical symmetries in the real world that we live. But we would be extrapolating if we just assumed that it would work the same way on another example.
Right. You know, I'm thinking out loud now because Keith has a very cool idea that would, I mean, is if there's any way you can quantify as you go real time in your epoch by epoch. I mean, you are measuring the extrapolation rate, let's call it. Maybe if you go to finite domains, like I'm really thinking out loud, real time. I mean, the exclusive OR function, okay, I can learn it with few examples. Here, extrapolation doesn't make sense because it's a finite domain. I'm just learning this table, right? So maybe that would be a starting point to measure extrapolation. I don't know. Because if there is a way to quantify how fast you're extrapolating and how much, wow,
that's an interesting thought because when you think about it, this in high dimension, right? We know that everything becomes far away, right? If you go to enough dimensions, every point they just become exponentially far away, right? And what's kind of funny about that, Walid, is that we think of discrete values in that way, or we think of discrete sample spaces that are not ordered like in that way, like you said, this table, right? It's just one point is as far away from every other point as every other point, right? And so maybe if we have a tool that this nice extrapolation measure that works in infinite dimension, it just no matter how it still continues to work, great. Right. Maybe it will work out of the box for discrete, unordered spaces, right?
Yeah. That's where the thought came from. Like because you will have a real measure of, man, I gotta, like in the exclusive OR table, good point. You have a point here and the other point is all over the place, has nothing to do with it. And yet extrapolation, perfect extrapolation, but okay, it's a finite domain.
Well, you can put an arbitrarily complex logical function in there, and then you've got like a hypercube of arbitrary dimension, and every combination is a point on a corner, and so they're all far away. But yeah, I just think we need some really nice measure of degree of extrapolation, 1 minus degree of interpolation, that continues to remain useful for arbitrarily high dimension.
Could I extend that thought as well? Cholet spoke about type 1 and type 2 generalization. So in the discrete domain, what kind of definition should we use?
Can you remind me again which type 1 and type 2? I'm blanking right
now.
Well,
Cholet is really into discrete program synthesis.
Symbolic discrete programs.
Yeah.
I remember.
So imagine we had, we're doing program library learning, and we have a whole bunch of sub-modules. And those sub-modules are, in some sense, capturing abstractions, and we can compose them together combinatorially. Right. So how could we say that those sub-modules generalize in a similar way?
They're the definition that I suggest that Keith didn't like would probably apply. It is, it is deduction there. There it is it's generalization, abstraction. Deduction, really. You're doing. I mean, generalization is one way of. Is also an inference in a way. So
okay, But neural networks don't do compositionality the same way as it happens in the discrete domain. We can agree on that. But some would argue, neural network researchers do argue, that there is a form of compositionality. There are neurons that represent, let's say, high-level concepts that are represented in our language, and they can be recomposed in some way. So how do you think that's different?
Look, I've written about this, but informally. Neural networks, every function composes. Every function is a function of inputs, and it does a composition, and it outputs a value. So, what's his name? Volodek Zadrozny, an ex-IBM Watson, now he's a professor emeritus somewhere, wrote a nice paper in the 80s that this vacuous definition of compositionality means nothing. Everything is compositional. Every output is a function of some inputs. So you're composing, okay, that's not where compositionality is. I wrote about this. And there were some episodes on compositionality and even a workshop that missed the whole point. I don't want to name names, but compositionality is meaningful if you can go back to the decomposition. Otherwise, if you don't keep the parts, the components, like 10 is compositional, but is it 2 times 5 or 6 plus 4? Compositionality is not about composing inputs into output. It is about decomposition, ironically enough. Neural networks are not compositional. Once you compose the inputs in a layer once you have a new tensor from all the inputs, good luck. You lost. The decomposition can be done in an infinite number of ways. You're done. It's like 10. 10 is a tensor, right? Did it come from 4 plus 5 times plus 6?
Yeah,
So,
that's the point that Fodor and Polishyn made, right? And
exactly.
their critical analysis paper is that
that's the crux of that classic paper. If you don't have the syntactic structure, you don't have compositionality, you don't have systematicity, you don't have explainability. You cannot tell me how you got here. Explainable AI will not happen in raw neural networks. I've written about it. You can. You need to explain how you got the output. That's explainable AI. You have to backtrack, right? Reverse your steps and tell me how you got here. That's explainability. You can't do this in a neural network. Good luck. Once you have a 0.98 at some point, where that came from, good luck. You're done.
Right. Yeah, and that was the entire point, and I mean, not the entire point, but that was one critical point in Fodor and Polishyn's critical analysis, is that...
But Keith, that's at the heart of the other stuff, in a way.
Yeah, I understand. I understand what you're saying, but I mean, that's exactly the point, is once you've taken in all these inputs and collapsed them into a real number, like you no longer...
And it's a real number. It's not even some variable, some symbol stored somewhere.
Right. And so what has to happen?
All you have is 0.89.
Right. And let me make a critical point here. One that I often try to make. One of the huge problems with that, and I'm going to speak really to concrete implementational level. Imagine you're a neural network and you're trying to solve a problem, okay? And you have to take all your inputs and always collapse them into a real number. And you can't store any parts because it's just a real number. As a consequence of that, what you have to do is duplicate like the inputs that went into that real number multiple times, so that you have like different calculations ahead of time. Because look, you can't store the parts, so you have to kind of do like every conceivable, maybe useful calculation of the parts and store them in advance in multiple values as a vector, because you might need them later on, right?
Actually, Keith, you would love this. Do you know the equivalence? I saw this somewhere else. Take a Boolean function. One way to prove its validity is through analytic method. Because we know what the implication truth table is, and we know when it's true or false. And so if I have if A, and if A then B, that's always valid. I can do it analytically because of the semantics of the operation. The extensional neural network equivalence is to build the full truth table all the time. You see what I'm saying?
Yeah.
Now,
Well, I mean, I think about it more in terms of arithmetic. So it's like,
yeah,
suppose I've
right.
got two numbers that are my inputs in my neural network, and
Right.
I don't know yet, for this data sample, if I'm going to need the sum or the product or the
Right.
difference or the ratio or like whatever. I have no idea like what I'm going to need. So I have to instead calculate every single thing I might need and store it in some, node somewhere
Yep.
that it can get passed on later. And this is why, so this is the critical reason why the computational, the effective with finite resources, forget about the axie infinite resource people, okay? Like in the real world, that's why like the calculations that one reason why the calculations that neural networks do, okay, and can do efficiently with a given amount of resources is radically different than what you can do with symbolic approaches. Like I'm not trying to say one is superior or
Yep.
whatever. I'm just saying there's a radical difference here, and it all comes down to this compositionality, which is not about convolving something into a real number. It's about keeping the parts around so that if necessary, you can reason about the parts.
Yep. Floridi said exactly the same thing. I have 2 and 2 and 4. Was it a plus? Was it a multiplication? I don't know.
That's a good way to put it. I like it.
Yeah.
Or here's a great example of a brain teaser. I'm just going to throw this out there. We're not going to talk about the solution, so listeners can work on it when they want to. But there's two guys, Paul and Sam. Paul knows the product of 2 positive integers. Okay, Sam knows the sum of the same 2 positive integers, and they're both former logicians, so they know math and everything like that. Paul looks at Sam and says, I don't know what the 2 numbers are. Sam says, I don't know what the 2 numbers are either. Paul says, I still don't know what the 2 numbers are. Sam, the sum guy, says, I still don't know what they are either. Paul, the product guy, says, now I know what the 2 numbers are. What are the 2 numbers? And when you work through like solving this amazing brain teaser, you're going to run into the same thing we're doing here, where we have to reason about the parts that are going into the possible sum or product. And even though there seems to be no information transfer, there is.
Is the key here that there are 2 numbers, not 1?
Correct. The key is that it has 2 parts, because I'll give you the first step. If the product guy doesn't know the answer, it means the 2 numbers cannot be 1 and a prime. Because if they were 1 and a prime, like say they were 1 and 13, the product would be 13, and he or she would instantaneously know, right, that it was 1 and 13. So it can't be 1 and a prime. And you work through this, right? But the point is, this reasoning requires reasoning about the parts.
The components.
Right? They have to know that there are 2 numbers, and they have to know that they're positive, integers or non-negative integers.
It's the same why transformers have to create a window of a few hundred words, because of the combination. I mean, they're trying to simulate the syntactic tree in a way. Neural networks do not compose. They are, it's a linear combination of the input, summation and product, and forget it. Where that stuff came from, good luck. I mean, there's no real composition. Composition is not computing an output from inputs. People talk about composition. It's a function of the component. Every function is a function of the components. That doesn't give me composition. Composition is I can go back to the components. I know where I came from. I know why I produced this. And that's why 3 times 5 is not 5 times 3. I need extra knowledge to equate these two. I need the knowledge of commutativity.
Talking about continuous.
Relationship between them. I thought he made it's obvious, but it's a brilliant observation, because before neural nets, I was interested in fuzzy logic, which the story goes, and it's true, it subsumes Boolean logic, which obviously, if you have 0 and 1, true and false, then fuzzy logic has them, but has everything in between. Okay, so that's why it was appealing. It's sort of related, even probabilistic logic, if you want. Okay, so yeah, that in theory, that's true. Not in theory. Effectively, it's true. The continuous subsumes the discrete. what we are missing here, okay, all my remark was that doesn't necessarily, that shouldn't make us feel good that we're in a continuous domain. Why? Because carving out that discrete function is really like looking for a needle in a haystack. Literally a needle. That's my function, this segment only. So try to find it in this. What I'm trying to say is that doesn't necessarily mean this paradigm can subsume easily the discrete. It contains it. But now go and look for it. So doesn't make the issue of discrete easier for neural nets at all, for discrete problems. I don't know if I'm making sense, but
well, we talked about something about this before, which is that there are these attempts at things like
right.
neural Turing machines and differentiable neural computers and things like that, where they try to program machines that have this iterative capability, an extendable memory that they can sit there and kind of iterate on for an unbounded amount of time. And exactly the problem is they're really hard to train, because what happens is they start trying to form these discrete functions, and then they end up with these really high gradients where they're trying to like cut off, a certain area, right? They're trying to create like very steep transition functions with high gradients in order to form these discrete regions on the manifold. And so once you have those super high gradients that are defining discrete areas, training becomes difficult, things explode, break down, etc. So I think this is, I agree with you, which is that when you can start continuous, but if you morph that nice smooth continuum into super high gradient, steep, discrete, sections, then effectively like you get back to all the same problems that people have had with discrete optimization, for example, mixed integer problems,
but,
things like that. Like all those things resurface.
Why does the training become difficult?
Well, imagine the data that I gave you is a square wave. Okay, like a literal square wave. So it has sharp, doot, 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 just a nice little pulse kind of train of square waves. Okay, and then I give you a bunch of continuous functions like parabolas. Okay, I want you to fit this data with second order polynomials. Okay, good luck, right? Good luck fitting that with second order polynomials, because you're going to have very high, coefficients on the second order piece of it, right? To get it to kind of bend up really sharp and make that corner, like fill in that little corner there.
Yeah. I mean, to summarize a little bit, we're almost saying here that it's almost an oddity of little relevance that the discrete is subsumed by the continuous, because we have the representation problem, as Keith was just saying, and we also have the learnability problem with stochastic gradient descent. So, and even if it was learnable, there's also this notion that what are we actually trying to learn? We're not trying to learn a discrete representation. We're trying to learn a function, and this is still in the model, the computational model of a finite state automata. So, what's the cache value, even if you could learn it and represent it?
Learnability itself, I can't imagine how it's going to. I mean, you are really your search for that function is going to be maybe non-compute. I mean, I don't. Yeah, right. So having, I think, Tim, you put it in a nice way. It's almost meaningless to say the discrete. It doesn't change anything in my mind. Yeah, I mean, theoretically, the continuous subsumes the discrete, but so.
Yeah, and well, the only way in which I find it meaningful is over in the the physics ontological side of the house that we opine about sometimes, which is like, it's clearly possible. It's clearly mathematically, scientifically possible that if the universe has some underlying, substrate deep down, it could be continuous, because you can get like for example, this is often so misunderstood, and it's kind of funny because it comes up all the time. The Schrodinger equation, right? The cornerstone of quantum mechanics is a continuous set of differential equations. Okay, folks, like it's 100% continuous. And the only way in which discrete anything ever enters like quantum mechanics is because you put in discrete boundary conditions. Okay, like you put in discrete boundaries. You say, okay, here's this continuous equation, but I'm going to put a particle in a box. Okay, and I'm going to pretend there's this infinite potential well at this little point here in space and this little point here in space. Now you get like discrete behavior now you get integer quantum numbers and behavior from the Schrodinger equation because you put in integers. Okay, like, so it's totally possible that the universe could be at the very fine level, continuous.
I mean, I
actually think, you can't argue the same thing. Like, you can't argue that a fundamentally discrete substrate can necessarily give you continuous behavior. It can give you approximate continuous behavior, like it may be below the Planck scale, whatever. There's some superfine pixelated, grid mesh, hypergraph, whatever of some kind, and we just can't detect like these artifacts because they're at too high of an energy. Okay, but in principle, there will still be artifacts. So a discrete substrate will always produce an approximation of a continuous.
Yeah, I was mentioning
substrate with
keyword defuzzify because it's about, there you put a boundary, and defuzzifying, you need a threshold. So no, defuzzify.
I'm sorry, I misunderstood you. I thought you said fuzzify.
You're putting a border, call it the threshold.
So I agree with you.
Imagine an image, color. You can go from that to grayscale.
Yep.
You're defuzzifying. You're saying, well, if it's light blue, I'm going to consider it white. So you're putting a threshold or a boundary, and you can go from the gray scale to just black and white and plot it as black and white and go to binary, 0 or 1. So same idea. It's a threshold or a boundary. But
well, I just would encourage anybody out there that's learning about quantum mechanics and or thinks that they know for sure that quantum mechanics is about integers and discrete numbers. Go look at the Schrodinger equation and find the integers for me, please. Like, go ahead. They're not there, folks. If you go learn some quantum mechanics, you find out, just as Walid said, they enter the picture because people defuzzify the Schrodinger equation by sticking in, boundaries, some type of compact. Use the math term there, but a compact region. Like you have to have a bounded.
Actually, that's what our von Neumann machines do.
For you to end up
1 and 0 are obtained after we have a threshold. Otherwise, the signal in the transistor is continuous. But we have a threshold, and we say, this is 0. Forget it. This is 1.
Yeah,
that's how all of computation works. Actually,
0.7 volts.
Yeah.
Well, and to me, there's something really deep and magical about that. And I don't know, maybe someday when I use psychedelics, like some more insight will come to me. But
actually, in the word of Lord, we have to defuzzify it.
We're going to have to hook
because
you
in
up.
the end, you have to make a decision, right? There's nothing called it's always fuzzy. No, in the end, you either take this road or you take this. So you have to defuzzify in decision making anyway. Which means you have to put a threshold and decide. Okay, buddy. I've been carrying all these fuzzy numbers with me for 3 hours. Well, now you wanna lift this or not, right? So at some point you have to defuzzify, otherwise your decision making will be unsound. It was proven. You'll get into funny stuff if you don't defuzzify to make a decision at the end. But
well, and this is connected to one of the deepest mysteries of all, right? Which is the measurement problem, right? The so-called quantum measurement problem, which is that, like, leaving aside many worlds, I don't want to go in a rabbit hole right now, but if you look around, okay, there is only one world. When you look at the cat, it's either alive or dead, i.e.
Right.
the universe that you observe, defuzzifies and comes to
At some
sort
let's
of
say at some point.
0 or 1
Yeah.
decisions, let's say, right? And well, here's the point I want to bring up here is mathematically that process, okay, of defuzzification, the same thing that, Walid here, is nonlinear. Okay? So quantum collapse, whatever you want to call it, decoherence, etc., it's a fundamentally nonlinear process. So just think, if I put a threshold in, a threshold is a nonlinear thing. You've got a value and the function is 1, and then boom, it goes to 0. Okay, that's a nonlinear process. And here's the real mystery, okay, of quantum mechanics is, again, look at the Schrodinger equation. It is a linear equation. It is a linear equation, okay? It cannot explain nonlinear behavior. And so one way or another, people stick in nonlinearity with some, hand wavy, kind of stuff. But there's a real mystery there as to how do we get from this linear behavior or linear model to nonlinear, behavior.
Actually, I read, I forgot where, but there was an interesting analogy between physics, the quantum, and the higher level physics. People compared it to the data-driven approaches and the higher level approaches, where you need a unifying theory. I mean, the analogy was so appealing that you either work at the lowest data level, that's the quantum level. The analogy here is neural networks. Or you have to, at some point, defuzzify and work at a higher level. And the problem is connecting these two. Nobody knows how you can come up with something that talks both ways. So some people, if you work in hybrid neurosymbolic AI, you're sort of working on the same problem, which is connecting the quantum data level with the higher level reasoning that you need to do. We can't dispute.
Right, and this happens all over the place. Like, nobody knows how to go from, statistical mechanics to Navier-Stokes, equation, so from particles to fluid mechanics, and from, quantum mechanics to political elections, and, whatever. And, and the whole, in principle you could do it. It's no. There's even, evidence that you can't even in principle do that. And you certainly can't do it in any remote.
When you say in principle, do you mean theoretically?
Reasonable scale.
We know we cannot. It is.
I can sense another emergence conversation coming on. So I think just before we go down that road,
I'll say this: it's all about singularities and the fact that your light cone and the fact that your light cone is always expanding.
How does this high level process emerges from? Because we know both exist.
We got to get Ulf in here to talk about this stuff when we go down this road, because we need our quantum mechanics, our resident channel quantum mechanics guy in here.
We've actually got Michael Levin on the show tomorrow.
This was fun.
Yeah, wow.
I read Gary.